About some really cool stuff today. The state of the art neuroscience with MRI is doing some incredible stuff right now, where we are on the cusp of what looked like science fiction like 10 years ago. And actually reading minds to a certain extent. We'll be reading some of the stuff that is coming straight from computers, just looking at brain activity. It's fascinating stuff. So stick through. We're going to kind of talk about how we got there through the first part of the episode, but there's some really cool stuff at the end. I'm Taylor Guthrie. I'm a social neuroscientist. I run the channel, the Cellular Republic, and I love having conversations with this guy.
And I'm Andrew Cooper Sansone. I run the channel Sense of Mind, where I make videos about neuroscience, about the brain and psychology, really trying to explain that on a interesting way. And Taylor's going to definitely help us do that today. This is going to be, I think, a mind-blowing topic for a lot of people. And yeah, it was definitely for me when I first started hearing about it.
There's some big players in the game now that are doing some incredible stuff, and a lot of it. I think something to really keep in mind through a lot of this is that this wasn't possible until very recently because it's very computationally intense. There's a very reciprocal relationship between the brain science, neuroscience world and the AI kind of machine learning, computer programming world, where we're helping each other. They're using what they know about the brain to create these awesome computer algorithms, and then we're using their awesome computer algorithms to understand the brain better. It's this really cool kind of reciprocal relationship that we have. And so we'll dig into how some of these top neuroscientists in the field are kind of using these advanced computational methods to really just look at your brain and figure out what you're thinking. And we'll talk maybe about some future applications for that. But I think where we're going to start is how did this even become possible in the first place?
Yeah. Yeah. And I mean, just if anybody didn't catch that, what Taylor just said is looking at your brain and figuring out what you're thinking, in other words, a very high tech version of mind reading. Like, we're not looking at a crystal ball. We're looking at a screen that's displaying data about what's going on in your brain, and then using algorithms to interpret that and figure out what you're thinking. But how did this get started? What is this all about, Taylor?
Yeah, so there's a term in kind of the neuroscience field called brain decoding. That's kind of the the a high-tech term for what is essentially turning into this idea of mind reading, of being able to just look at the brain activity and be able to predict what it is that that brain activity actually means. And so I think it's really important to understand that the brain maintains representations of the outside world. And I think this is something I really like contextualizing a lot of this stuff, bringing it back down to kind of the nitty gritty, to the ground level. Uh, Individual cells have representations. We've seen this in bacterial cells. Bacterial cells have certain configurations of the molecules that can actually predict future states of their environment, future nutrient states, future temperature levels, all of these kind of things. It's kind of early level cognition, right? But that tends to be, at least on the low level, tends to be very kind of Pavlovian in kind of the philosophical terms. They call them mere associations. That you have something that happens in the outside world, and you have this connection to it, and you somehow have this representation that those things are connected to each other. But as things got a lot more complex, we started, especially as humans, with language, with all of this stuff. Our brain is able to create these incredibly detailed representations of the outside world, of specific objects, of specific categories, of specific psychological ideas and symbols. And essentially, what we're trying to do is we're trying to crack the neural code, right? We've already tried to crack the DNA code, right? We've tried to crack codes in wars in times past. Ultimately, what it is that there is a certain type of information that the brain is using, and we're trying to figure out kind of what that schema actually looks like. And so, if we can see, like, okay, when these things fire in this way, that means chair, that means house. That means I'm a good person, or I want to do something nice for someone. Um, those are actual examples of things that have been decoded from people's brains. They found specific parts of the brain that are like uh, pleasantry type stuff. Like this part of the brain lights up when we're thinking about thanking people or saying please or whatever. Uh, but where all of this started in terms of being able to do this stuff was with a man named James Haxby, and he's at Dartmouth. Dartmouth is very much considered kind of the birthplace of cognitive neuroscience. There's a very famous neuroscientist, Mike Gazzaniga. If you've ever had a brain class before, your textbook was probably written by Mike Gazzaniga. They started this whole thing at Dartmouth, and Haxby came along and said, I think that we can start using these new computational methods to really look at what the pattern of activity actually means. And a lot of this was kind of taking a very sharp turn away from how MRI was done. And so I think we can maybe kind of start there if you want to. So,
Yeah.
so traditionally, the way that MRI is done traditionally was that we stuck someone in a scanner and we had them do some type of cognitive task, right? So they were trying to remember something, or they were paying attention to something. They were looking at specific types of objects, and what we were trying to do with these original things was see what areas of the brain were the most active for these things. And so you have them do something, and then you have them not do something, and you're doing what's called a contrast. You're saying, where is there more activity when they're doing something than when they're not doing something? And what you get from that are just these kind of peak activity values of like these regions were the most active when someone was doing something. And that information is really useful and has been really useful for a while now. It's told us a lot about these individual parts of the brain that are involved in certain types of cognition. So when you're remembering things, the hippocampus lights up. It has this really high activity, right? And that's opposed to when you're not trying to remember something. Um, and there's also a lot of so there's a big debate in the field between someone named Nancy Canwisher and James Haxby, who I mentioned, who has developed kind of this new technique that's gone on to create this mind reading ability. Uh, Canwisher found what's called the fusiform face area, and so this is an area of the brain that when you show people faces, as opposed to showing them a chair or a dog or whatever it may be, that this region gets really active. And so a lot of the neuroscientists with these kind of traditional MRI experiments have really taken this kind of localization type stance. Of there are a couple of really dedicated regions in our brain that do very specific things. This thing just lights up for faces. There's another region called the parahippocampal place area that seems to just light up when we're seeing places, houses, scenes, these kind of things. There's another area that lights up when we see body parts. And so it was this idea that those regions just care about faces, just care about places, right? And so this is where this new kind of technique really kind of got its start because James Haxby came along and said, what if we can look into these regions and actually, instead of just saying this is on when someone's looking at a face, we can actually peer into that area. We can look at the different levels of activity and we can see exactly what they're looking at and see whether this region is just caring about faces or whether we can also kind of see if it's carrying information about other things as well.
And they did find that, right? They found that there was other kinds of visual representations of other kinds of objects could be found in the activity of the fusiform face area, right?
Yeah, so this was kind of his first foray into this. He said, instead of just looking for what's on, let's see if we can do something with the pattern of information. That instead of just looking for these peak activity levels, we're going to say, let's use these new kind of computational techniques to say, what is the constellation of activity? So this little area of the brain right here is like really active, and this one's kind of active, and these ones kind of have a little bit less, but this one's really high. And it's that whole pattern that contains the information that means something. It's not just that something is really active, it's this whole constellation, this whole pattern that actually constitutes what it is that's being kind of processed in that moment. And when he took this approach, he looked into these areas that were supposed to just be for faces or just be for places. And he was able to, with incredibly high accuracy, I'm talking like over 90% accuracy, tell whether or not someone was looking at a chair, whether or not someone was looking at a shoe, whether or not someone was looking at a house or looking at an animal. So there was information in this area that was supposedly from these traditional MRI experiments, traditionally just for faces. He was able to find information about all of these other things. And it was this first example that, wow, we can take this pattern of activity and actually predict what someone's looking at. Not just like this from the end and saying like we know what they're looking at, and we have this area that's really active, but just looking at the brain activity, we can say they're looking at this category or this category or that category.
And what was kind of the rebuttal to that? Why is the debate still going on today between Canwisher and Haxby?
Yeah, yeah. Um, so this is it's fascinating stuff. This debate has been kind of swinging back and forth for a long time. So if anybody that's listening has taken kind of an intro psych class, you've probably heard of Franz Joseph Gall. He was the guy that did phrenology way back when. Basically looked at people's skulls after they died, and he had these like there was these little divots, and he was measuring all of the divots in the skull, and said that that brain activity is very localized. That there are specific areas of the brain that do very specific things, and his categories were ridiculous. It was like there was one area of the brain that was just for familial piety, uh, just bizarre stuff. But he very much kind of started that idea that there might be some kind of localization of function. And when you look at the brain, there's a visual cortex that just processes vision. There's an auditory cortex that just processes auditory information, right? There is some level of localization, but over the last 200 years, this debate has gone back and forth. So after Franz Joseph Gall, there was a guy named Florenz that did work on pigeons. That was just like no, there's not localized function because you can like zap all of these different parts of the pigeon brain, and he's still able to do all of these things. And so there's really more of this kind of like whole brain activity. The whole brain is involved in cognition, and that it's really more about just kind of the how the information flows and how that pattern unfolds. And then Brokaw and Wernicke came along, and they were like, "Well, I found this area of the brain that's very specific for language. I have this patient that when you take this out, all he can say is tan, and it's just this one region." Uh, right? And so it was this again. It was like, okay, well, maybe there is this localized thing, and so that's where we're at right now. Again, with this kind of Nancy Canwisher and James Haxby, is uh, whether or not there is kind of localization of function, because that's what Canwisher is saying, that there are these specific regions that care about faces, that care about places. And Haxby came along and said, well, that can't be true because I can find information about everything in these regions. And so where the kind of rebuttal is that there may be information that we can decode in these regions, that information flows through all of these about all of these different things that we see in life, right? You see a shoe, it's going to go through the entire vision pathway to the regions that kind of determine what it is and all of these things. But what may be happening is that there are specific regions that are like red flag detectors, that like all of the information is flowing through there, but then all of a sudden a face comes through and it's like, oh, hey, this is really important. You should pay attention to this. And so it's really more about what's actually getting to conscious awareness, right? Because like
Yeah.
our brain is processing billions of bits of information at any given time.
Yeah, and it I mean, the thing that struck me is the kind of neurological data or the neurology data where somebody will get really localized damage to this certain segment of the fusiform face area, and then they're not able to perceive faces, but they're able to perceive pretty much everything else, or at least that's the claim. But I mean, nevertheless, like that information is still the information about those other objects still seems to be encoded somehow in the activity of those areas, even if it's not making its way to consciousness. And that's kind of the larger point, I guess, of what
Mm,
we're talking about. The information is there, whether the brain sends it to awareness or whether it doesn't. Neuroscientists can now like kind of look at that activity and get some meaning out of it, whether the brain is doing that or not. But maybe we could, if you want to take that from there, what direction you want to go
yeah.
in.
No, it's I think you make a really good point. Because yeah, there have been these really clear indications that if you knock certain areas out, that it stops this. But what we really care about, and especially for kind of in terms of the episode, is the fact that we can actually decode, that we can crack the neural code to a certain extent. And that's what Haxby is it started to show, and he created this whole method that has now just blown up in the neuroscience field with MRI researchers. And there's a technique called multivariate pattern analysis that arose from this. And so it's how we basically, when you put someone in an MRI, uh, the scanner is taking a picture of their brain every 2 seconds. And every 2 seconds, it's taking these activity values in like 250,000 different areas in the brain, and they're in these little cubes called voxels, and they're about 2 by 2 by 2 millimeters. That's like the lowest resolution that a lot of people go to. And so essentially, what you end up with is all of these little cubes of the brain with specific activity values associated with them. And you can take every single one of those little cubes together as a whole pattern of activity. Instead of just looking for which ones are the most active, you can take an entire swath of them and you can turn it into a vector of numbers essentially. And you can just say, is this pattern of information, these ones high, these ones low, these ones kind of in the middle, is that kind of carrying any information about this internal representation that this person has? And I think it's really important to highlight the accuracy levels in the Haxby papers. I mean, so this started with what's called categorization. So they weren't trying to actually decode from someone's brain the exact thing that they were looking at, but they were looking at whether or not they could predict what category of information they were looking at. And so these original studies were like, okay, we had 6 different categories. We had tools, houses, faces, animals, and shoes, or something like that, right? And with greater than 90% accuracy, just by looking at the brain activity, he could determine which of those 6 categories you were looking at. Which, I mean, chance is pretty low. To be over
Yeah.
90% means that you're like on the money.
And he was looking at all across the brain, right? He was looking at all the so taking, like you said, the voxels, the cubes, split the brain into evenly sized cubes of 2 by 2 by 2 millimeters. Is that what you
Mhm.
said?
Yep.
And then you look at, you kind of reduce all brain activity to just an array of numbers that corresponds to the value, like the activity in each of those voxels. And then he was able to get to predict, to estimate what category of object people were looking at just by looking at the values of those the activity of those voxels.
Just a bunch of numbers.
It's
It's
crazy.
just numbers. Yeah, and so, uh, I think the really surprising thing there, especially from Haxby, was that he didn't think that he was gonna have this really strong specificity between different, like, similar categories, like shoes and chairs. They're both man-made objects, right? But somehow there was this really distinct activity between these categories of shoes and these categories of chairs. Uh, and when you really think about the category stuff is really interesting because that's how our brain kind of works. We have like prototypical representations of things, right? When you think about a spoon, you don't think about every single spoon you've ever seen before. You have this like this prototype of like all of the spoons combined into this perfect spoon. And that's essentially what he's picking up on.
And that's amazing because yeah, those are I mean, they're not, like, natural kinds. They're just, different objects that we look at, and then we kind of somewhat arbitrarily as humans just categorize them into, different things, but
Mhm.
it's incredible that he was able to pick up on that.
And that was, I mean, that was just the beginning. That was like 15 years ago, almost 20 years ago. And this kind of computational method has just kind of blown up in neuroscience. And so it's very much it started in this kind of like, can we categorize things? And it's very much moving into more of kind of an identification type thing of like instead of just saying like, okay, are they looking at a house? Are they looking at a dog? What house are they looking at? Are they looking at the yellow house with the red door, right? Are they looking at the Chihuahua? Or and the accuracies for this are starting to blow up as well. And I think that kind of leads into some of the really really cool work that's being done now um, from from other people in the field.
Yeah, because if people are listening to this and thinking, well, that's not really mind reading. It's just kind of sussing out, one really narrow part of your experience. Like, are you looking at a greenhouse or a blue house or a dog versus a tool? But it does it like in a very short time, it's gotten a lot more advanced. A lot, I mean, a little bit creepier, I think, as
Mhm.
it's gone on. But yeah, you go ahead. I mean,
Yeah, yeah. So Jack Gallant is really who has done some of the ones that when you watch are fascinatingly creepy. Um, so I think something really important to keep in mind through all of this is that this requires a lot of data. And it also requires that we put you into a $2 million magnet uh, and scan your brain for hours so that we have like tons of brain activity to actually work with. So this is not at the level yet of like people on the street just like, oh yeah, I can read your mind. And no, this requires very specific tools to be able to do. But it's a proof of concept. And so Jack Gallant, he created what are called voxel-wise encoding models. So this is kind of a different approach than what I've talked about before, and it sounds very jargony. I'll like simplify it. So the whole idea is that we know. So Jack Gallant was a vision researcher, and vision research is like one of the most popular fields of research in cognitive neuroscience. We are extremely visual creatures. The visual cortex is really kind of fascinatingly profoundly organized in a really cool way. We have these spatial receptive fields. So basically, there are very specific neurons that will only fire if they see a line at a specific orientation at a very specific point in space. Uh, and we've mapped this out in all kinds of animals. We've gotten MRI data that kind of maps on and shows that our brain is very similar to these other animals. And so we know really, really well what the early visual cortex is doing. It has this map of the world, and we know how that map works. And so, because we know how that map works, instead of starting with the brain activity and trying to predict what it is they're thinking about, he said, I'm going to start with the actual stimulus. I know that this picture that I'm showing you has these lines and these orientations, and that it's probably going to make your visual cortex do something very specific. And because we know really well how your visual cortex works, we can create these models that say if if we see something that looks like this in the brain activity, then it's probably that picture. And so by doing that, by doing the kind of this backwards approach of using the stimulus and creating a model of the world, and then saying this is what we should expect from the brain, uh, they're able to actually like recreate what you're watching to an eerily creepy level. So you can. So for those of you that are watching, if you just YouTube Jack Gallant, Gallant, There's all kinds of YouTube videos of it shows the actual video that someone's watching, and it shows the recreation that is being made just from the brain activity. And it's not exact, but it's eerily similar.
It's like if you drop some acid and then you like
Right.
imagined like watching a movie. It's just this like psychedelic version almost of what these people are watching. So it's, they're someone's watching a movie, right? And then they're scanning their brain, and then they're taking that brain activity and trying to use it to recreate that movie. And you would think like, oh, that would just get so jumbled and it would just look awful, but it is amazing. Like it's we'll definitely put the link to those or at least one
Mhm.
of those videos in the captions, because it's pretty amazing with the how accurate these, even though they're blurry and they're not exact, and sometimes it's off. It's pretty amazing that they're able to get that level of detail. And that's just from the primary visual cortex, is that right?
The original ones are, yeah, yeah, yeah.
Okay.
And I know that they've made some improvements with the way that they're doing things. They and I mean, like Andrew was saying, I mean, if there's a person on the screen, there's a blurry person on the other one. If there's words on the screen, there's blurry words on the other one. Like it knows between these categories, and there's a scene of elephants walking across a field, and then there's this like sketch of elephants walking on the other one that's just from the brain activity. I think something that's really important to highlight here is that we're doing this with MRI data, which is extremely noisy, right? So we're not measuring direct brain activity. We don't have these electrodes implanted in someone's brain where we're reading directly from the visual cortex. Uh, my camera, oh, there we go. But we're looking at blood flow. So with MRI, we're using what's called the bold signal. So when neurons fire, they use resources and they need to be replenished. And there's this really fascinating thing that happens in the brain, that blood replenishment is localized. It only happens to the areas that need it. And so we know by looking at where blood goes, what regions were just active. But there's a huge lag. There's like a 4 to 5 second lag. So, like, if you're thinking about actual brain activity, that's milliseconds, right? So we're looking at activity that happened like 4 seconds ago using some blood measure that's not actually activity, and from that we're able to recreate what someone's watching. Like that's fascinating.
It is fascinating. And I guess it sort of raises the question of if is it all, and I think this would be the can wisher kind of maybe interpretation of some of this would be like, I don't know if she's actually said this, but like, is it just correlation? Like, are we just, of course the brain activity is going to be different when you watch a movie versus, or with this movie versus that movie. But are we really getting at like the brain is actually using that same code that we're deriving to create your experience? Or is it we're just looking at this massive activity and we're kind of able to recreate something sort of like the original stimulus, but it's kind of happenstance. It's not exactly what the brain's doing.
Yeah, no, I think you're touching on something really important, because a lot of this work is again looking at these early processing regions, right? Uh, Early visual cortex is the kind of first processing stages of any type of visual information that we're looking at. But before it actually gets to conscious awareness, it goes through an entire pathway to these very complicated regions of the brain that are combining information from different senses and creating these kind of holistic representations. Those regions we don't have as much kind of detailed information about. We don't know like those neurons in these areas that are really complicated, these what are called multimodal, that they integrate information from sound and from sight and all of these things. They don't have these really clear receptive windows like neurons do in the visual cortex. So they don't fire for a very specific line at a very specific orientation. They fire for lots of stuff. And so trying to figure out and how to decode that kind of information gets a little bit more complicated, but we're also kind of on our way with that. And I think that's a good transition into some of the language stuff, because So Jack Gallant's lab has produced some amazing scientists. His students have gone on to do really amazing things. And one of the kind of stars from his lab was Alexander Huth, who kind of veered away from the vision side of things and wanted to get into language, into semantics. Because I mean, if we're talking about mind reading, then we really want to read out what people are thinking in terms of actual language and words. And the very first applications of this were pretty amazing. They were still using the videos, but they would have these word clouds up. And as the movie was changing, you could see the word cloud, certain words would get bigger. So if there was like a man on the screen, the word man would start getting bigger. If there was like a surfboard and a beach scene, you'd see this word like beach and surf and things starting to get bigger. And that was just looking at the brain activity. These words were kind of picking up on this activity. And uh, but that was just the start. And Alexander
And
Huth, yeah, go ahead.
sorry, and how did they? I mean, I don't. Maybe we're about to get to this. I don't want to derail you, but how are they able to do that? Go from looking at a movie to a word cloud. Like, what was the? How did they connect those two things? Um,
So they were starting to kind of branch out into these other regions of the brain and starting to look at. So I have a specific word, and what I can do is that word has a certain kind of properties to it, and I can go across the entire brain, like voxel by voxel, and I can say, what word does this voxel care about? I can create these models where I'm like, if this word is present, or if a depiction of this word is present, does it make this voxel do something? Does this care about this word? Right? And that was kind of the original things that Alex Huth was doing, and he did this across the entire brain. I We'll have to link his. He's got a website where you can go, and he's got the entire brain and all of these words that he used. He used like hundreds and hundreds of words, and you can see which areas of the brain care about which words. Like, and I mean, words is as crazy as like platypus. But what he found, I mean, he had to simplify that data a little bit using what's called principal components analysis. There's tons and tons of words, but you can kind of categorize those words into certain categories. And so there's certain parts of the brain that care more about social words than about words that represent specific objects or tools. And he was able to look across the entire brain and map out the entire brain, all of these different regions that cared about certain words. Um, and that was his first foray into this, which is amazing. And it kind of created these cool word clouds and everything. Uh, but his lab now is taking that to the next level. It is absolutely insane. So instead of just looking at kind of what words certain regions of the brain are interested in, they kind of transition now into like word phrases. So instead of just like the word thank or the word sir or the word whatever, they have an entire. They're having people. The way that they do this is they have people listen to entire stories, and these types of experiments require tons of data. And so they're a lot different than other MRI experiments. Other MRI experiments, they usually bring in like lots of participants and get like a little bit of data from a lot of people. These ones actually take like 7 people and just get like 10 to 20 hours of MRI
yeah.
data on them.
It was like what? Like they were listening to the podcast, the Moth Radio Hour, right?
Hmm.
And they listened to up to 101 episodes of that while
Yeah,
in the scanner. That's a huge amount of data.
a lot. That's sitting in a noisy tube for a long time. But it is one of the more pleasant MRI experiments. I've been in an MRI a lot. And you actually get paid. So anybody listening, if you live near a university, they pay like $20 to $30 an hour to go do these experiments. I made like $500 one month just sitting in a scanner.
Jeez.
Um, but
That
a
is your
lot of those
full-time job.
experiments. Right? No, I was trying to supplement my really small grad stipend, uh, but a lot of the MRI experiments that you do are really kind of unpleasant. and I'm not trying to deter everybody after I just told you to go make money, but a lot of them, you're doing things that aren't like fun. They're having you like remember that this dog was connected to this ball, and they're trying to figure out like what the memory systems are doing while you're doing that stuff. These experiments that we're talking about are actually enjoyable. You sit in a scanner and you just listen to podcasts for like hours, and it's a little uncomfortable. You're in this kind of like confined, noisy tube, but it's a lot easier to get through, and so they're able to have people sit there for hours and hours and collect this data. Um, but yeah, just from the brain activity, listening to these stories, they're able to now take like entire phrases from the story and say like, instead of just looking at the individual words and what areas of the brain care about these individual words, the brain is making sense of long-term information, right? We don't just care about one word in a sentence. We care about the meaning of the entire sentence, right? And there are some areas of the brain that care more about like an entire sentence than like one word. Like early auditory cortex is processing just like frequencies and sounds, and so it's probably going to care more about like individual words than a more complicated part of the brain, like the frontal cortex, that's putting that all together and is actually saying like, okay, this sentence has noun verb agreement, it has some specific meaning, it has context within the larger story, and our brain is tracking all of that. And so that's really what he was trying to get at, was like, okay, are there these individual phrases that may be kind of encoded in these different areas? And he did this analysis where he said like, how much better are these models that use phrases than the models that use words? And it was just like crazy better. He shows this map that's just like, so the areas in blue are the areas that the word models do better, and the areas in red are the areas that the phrase models do better, and the entire brain is red.
It's yeah, it's it's amazing, and then what they were able to do with those phrases, right? They kind of did similar thing to what Gallant Lab did, where they took the activity and then tried to recreate the video, and then the Huth Alexander Huth's work did something similar to that, right?
hmm So, so they had started by just seeing like what regions of the brain care about these different phrases, um, and this was still kind of using this encoding. So they knew information about kind of words and about the flow of words, and they're using like really big things from the data world. So, in order to do this, you have to have a really strong model of how language works in general to then kind of say, we know how language works, and if this is how language works, this is probably what the brain should do. And that's coming from these AI algorithms that are predicting what you're going to text next. If you're sitting there texting and you see what word is coming up next, these are these natural language processing algorithms that they're now using to predict brain data. They're used for like AI chatbots and all of these really cool things. Um, and so they used that at first just to see what areas of the brain cared about these different phrases. But then another one of his students was like, I want to go back to this decoding idea. I want to just look at brain activity and see if we can actually recreate the story that someone's telling. Um, and they kind of used these really kind of fancy ways of combining these different models. And I'm gonna read some of these to you because they are they're so fascinating. Um, so this is the actual stimulus that someone heard. I didn't know whether to scream, cry, or run away. Instead, I said, leave me alone. I don't need your help. And this is what the AI predicted just from the brain activity. Started to scream and cry, and then just said, I told you to leave me alone. You can't hurt me. And so what you're kind of getting from that is that the words themselves were different. Like if you look just at words that the AI is predicting, it's actually pretty terrible. But if you look at meaning, it is incredibly precise. So there's examples. There's definitely stuff that's different. That's like missing. Um, so in the actual stimulus, he said, "I don't need your help," but in the decoded one, it says, "You can't hurt me." So that was kind of different and off, you know. But then there were some things that were exact phrases: scream, cry, scream and cry, leave me alone, like exact phrases. And the really cool thing, the way that this actually works, so I mentioned how MRI is this really noisy measure, right? We're looking at blood flow. There's this huge time lag between when someone actually heard something and when we're actually picking up the signal. And so there's the possibility that there may be like 40 words that that signal is actually representing. So the ability for us to actually say like an entire phrase comes from like, okay, the brain activity predicted these words, and then these language models are like, okay, but do those words make sense in a natural language order? And so it's taking what the brain activity might be saying, and then it's combining it with these language models to say like, okay, well, is that something that we would see in a natural language, in a natural sentence? And it's using that to create this recreated story. And it's fascinating how. So I have another one here. I don't have my driver's license yet, and I just jumped out right when I needed to, and she says, "Well, why don't you come back?" That's the actual stimulus. This is what the AI read out. She has not even started to learn to drive yet. I had to push her out of the car. I said we will take her home. So again, here you're seeing these elements that are incredibly precise. And one of the things that's really fascinating from this one in general, the original stimulus never mentions the word car, and the AI does. The original stimulus mentions a driver's license, mentions jumping out of the car. The AI says that they were pushed out of the car, but the AI actually uses the word car. And so it's picking up on the fact that whoever was listening to this story had this internal representation of a car because they knew someone was talking about a car. Like,
And
we
that's
told you we were
where
going to talk about mind reading.
right, and that's where it's crazy. It really it crosses the boundary of, we're just kind of figuring out what your senses were picking up on into really getting kind of closer to decoding somebody's subjective experience, because
Mhm.
it's now getting into this like subtle idea of meaning and connotations and these associations between things rather than just the literal playback of what was hitting your ears when you heard that sentence.
And I think you touched on something really important because when we're talking to one another, we're not analyzing every single word of the sentence that we're saying to one another. We're at the end of that sentence, we're kind of collecting this kind of gist information, right?
Yeah.
And so we're creating a representation of that concept, of the meaning of that word, or the meaning of a couple of words in a phrase, and that's what we're picking up on. That's fascinating.
Yeah, it's incredible. I feel like we have this ability to like get the gist out of things and get you know our brains are prediction machines, right? So we're always kind of trying to predict what really what's happening in the world around us and what it means. We just experience that as our moment to moment experience of reality, but it's
Mhm.
really at least in part it's this predicting of what's supposed to be happening. And as you were saying that, I mean, it reminded me of this quote from a language scientist, Steven Pinker, where he wrote out the sentence, and it said, our brains are so, or something like, our minds are so good at decoding symbols that you can read this sentence with all the vowels removed, and it's all of the vowels are replaced by x's, and you can completely understand, like you can, it's
Mhm.
clear as day what he's trying to say.
Yeah, and that hits on something that's, I think, really big in kind of the neuroscience philosophy world right now is like, what is a representation, right? And that's ultimately what we're kind of getting at is, uh, are there such things as like these internal pictures, these internal kind of uh, coded messages. And essentially, I mean, the DNA code is only made from four different letters, right? ACTG. Uh, the neural code is a lot more complicated, right? And it's able to combine these incredibly complex symbols with one another and create this kind of psychological meaning that we give to our lives and all of these things. And for a computer program to be able to look at a bunch of noisy data from blood flow and pick out that meaning, um, that is the start of cracking that code. It's not perfect, But I mean, they're even like Alexander Huth went on too to like just show movies, and they have the AI just like reading out what's happening in the movie. So they're not even listening to things; they're just watching a visual depiction. And the AI is like just it's not perfect at all. Give me that. But a lot of the same meaning is there. That it's like describing things that are happening on the scene. That like there's this the video is really weird. It's like some woman like taking care of a baby dragon that's hurt, but the AI is just like blood and gasping for air, and like is describing that there's like something in distress on on the screen, that needs help, that's like getting care, and it's like reading out these things that are just like eerily connected to what's going on the screen.
And I kind of wondered when watching that part of the video, um, like when people are paying attention to anything, especially for a long time. I think all of us are familiar with reading a book, and especially a book that you're not that interested in, and you get to the end of a page and you're like, oh, I don't remember anything that I just read. I couldn't tell you, what just happened in the last 5 minutes of reading, but like you're still reading it somehow. And I'm wondering if some of that like is kind of making this data noisier. It just occurred to me that like as you're watching this video and then all of a sudden you start thinking of what you're going to have for dinner tonight, like the AI
Mhm.
might actually be picking up on that activity, but I
Yeah, no,
yeah.
you're actually onto something, and they've actually done some experiments that are looking at this. Because what we kind of started this whole episode with was talking about this kind of Haxby Canwisher debate, of like, okay, we have this activity that we can pick up on, great, that's information. Is it actually being used? And there's actually kind of in line with what you just said. There is research that's showing that we can be picking up on the information that's actually being used. So they did kind of there's the cocktail party effect. So if you're at a party, you can selectively attend to different auditory streams, but you can't attend to multiple. So you can listen to what I'm talking about right
Mm.
now, but then you can't also listen to a story that someone's saying across the room. Or you can like completely tune me out and just pay attention to that story that's happening on the other side of the room. So they've done this where they put like one story in your left ear and one story in your right ear, and then you're told to attend to one or the other. And with these, they're actually decoding which one they tell them to pay attention to. So if they pay attention to the left one, then the decoder, the AI algorithm, is reading out information just from that one. And if they're told to pay attention to the other one, the AI decoder just picks up information from that one. And so I think that they are now tapping into the things that are actually at awareness. And I think you touched on something really important, that mind wandering definitely comes to play here. But it's also a tool to fight this.
It is. How
It
so?
Yeah. So, I know a lot of people listening, a lot of this stuff can get kinda freaky and kinda eerie, right? Like, okay, they're doing this with this, like, $2 million magnet, like, what if technology advances, and what if they're able to do this with other devices, right? Can they just read our brain activity in general? And so they did some studies kind of on the back of these attention ones, saying, can people actually prevent someone from reading their mind? So they had them listen to these stories, and they were trying to decode what the story said, but they told the participants to like count backwards from 100 or multiply by sevens, to do something that was not related to the stories. Don't pay attention to the story, pay attention to this kind of like internal cognition that you're working on. And it prevented the AI from being able to decode. So
Wow, yeah.
you can protect your brain activity.
You just have to kinda constantly be thinking random thoughts and essentially go crazy. That's
Uh,
all.
but I think this very much does bring up some very strong ethical concerns coming forward, because I know a lot of the listeners probably are aware of Elon Musk's wizard hat, as he calls it. It's his company Neuralink. So they've created these very fine fibers that are smaller than the width of a hair, that robots can implant down into your brain. They've already implanted these in monkeys. They've implanted these in pigs, and it's really interesting because I've talked about this with some of the people in the neuroscience community, and everybody thinks that it's just like just bullshit and it's not gonna. And I'm like, how can you say that when we're able to decode things with blood flow from this really noisy MRI machine? And you're now saying that we're putting direct electrodes into someone's brain that's recording the exact activity at the exact time that it happened. Uh, that has extremely high potential for being able to do these things at a precision that is light years ahead of where we're at right now.
Because they're actually recording neural activity, like individual neuron, well, thousands of neurons,
Mhm.
and that's yeah, that has to be kind of the next stages of this. And I mean, yeah, I don't know if Neuralink. I feel like people don't like Elon Musk generally, and then anything he does is like, oh, it's stupid, it's not
It's
real.
so
But
stupid.
it's not just him. There's other companies that are doing this, and there's just more and more research into this, like direct, recording of brain cells actually firing rather than the blood flow measures.
Mhm.
But I was always wondering, like, if combining those would yield some really interesting results, especially, um, just considering the different time scales and different kind of variables that they're measuring. If they could get a more holistic picture of what's going on in the brain.
And I know that some of these people that do this work have ventured into the ECOG world. So a lot of people might be familiar with EEG. So they put these kind of electrodes on top of your head, and they're trying to. EEG is really good at saying when something happened. Something happened right now within millisecond precision, but it's really bad at saying where it happened. And a lot of that is because it's on the outside of the skull, whatever. But there are people that need surgery for epilepsy that will have their brain completely exposed, that instead of having the electrodes on the outside, they'll have them directly on the brain. And some of these people have been doing this kind of decoding work with that type of technology, and it's pretty incredible what they're able to do with it. Um, I think the kind of Elon Musk stage is even a step further. And there's actually, as you mentioned, Andrew, there's a lot of companies that have actually been doing this for like over 15 years. And some of the minute ones have ones that hook right down into your motor cortex, and they're able to read your motor intentions. And there's these fascinating videos that you can look up of a woman controlling a robotic arm just by thinking. Um, and they even ask, there's like a famous news broadcaster that was like having this like talk with her, and he's like, well, what's going on in your brain when you're moving that robotic arm? And she says, lift your left arm. And he lifts his left arm, and he says, she says, what was happening in your brain when you just lifted your left arm? And he's like, nothing, I didn't even think about it. She said, exactly, that's what's happening here. So this device somehow has like integrated itself into her just like natural way of moving, and she's able to grasp things, move left to right, bring things to her, and drink like crazy.
Yeah, yeah, and I like there are a lot of there's like David Eagleman. I think his lab does a lot of this stuff, trying to kind of like basically give you a or extend the human body into these machines by hooking them directly into the brain. And it's been
Hmm.
going on with stuff other than just motor activity, with maybe starting with like artificial retinas that
Hmm.
that people have been able to restore sight to somebody who has a damaged retina by replacing it with this synthetic version. And I mean, that's a lot different than decoding the brain activity. But it does seem like as we progress in this, we're kind of able to integrate new kinds of technology. And that was some in a book I know that you've read, and I would definitely recommend to listeners, David Eagleman's book Live Wired,
Yep.
where he starts talking about the future potential for the kind of sensory stuff that we're talking about, where you could he's got this crazy idea where you could have these sensors, like sensing your blood pressure and all these different physiological variables, and then feeding that directly into your brain so that you could become consciously aware of all of these biological processes going on in your body. And I don't know, supposedly do something with all that information. But it's and tons of other crazy applications as well.
No, and I think that you're very much kind of on to what we need to start thinking about because we're on the verge of some really crazy breakthroughs in this technology. And what are the things that we need to consider? What are some of the ethical implications? I really like too that we're not just highlighting kind of some of the scary stuff, but this if we understand the neural code, we can restore function to people. We can allow people to see again that were blind and allow paraplegics to walk and deaf people to hear. Like that's incredible just by having kind of uh, an idea of what the brain activity means and how we can kind of give it to the brain. David Eagleman is he's one of my idols. I love David Eagleman, but he has this fascinating kind of way of talking about the brain. That the brain is just this 3 pound thing in this dark cavernous skull. It doesn't see light. It doesn't hear sound. It doesn't touch anything. All it gets are neural impulses, just patterns of information, right? What we've been talking about through this whole episode. And what the brain is really good at is just making sense of patterns of information. And so he's done a ton of really cool work that shows if you just give the brain patterns, it will make sense of them. And I really like what you just mentioned. I mean, it very much fits in with, I think, my view of what the brain is responsible for, and it's responsible for taking care of the body. And I think that the brain has a big disconnect between a lot of the health factors that a lot of these new technologies can help with, that they can actually start telling us whether or not we need to eat more fruit or whether or not we need to drink more water, and can give us like actual feelings and actual like representations that that stuff is happening and that we need to take care of ourselves and be more healthy. So yeah,
Yeah,
there's really cool stuff.
like just to jump on the back of that, he also he talks about this idea of like plugging it into um like stock market data and stuff like that so
Mhm.
that people could directly plug into like what's going on the New York Stock Exchange, and stock traders and others could kind of really get an intuitive sense for like what the patterns mean and what's going on and when they should buy and sell. And it gets very
Yeah.
sci-fi, but like I don't know, I mean, I don't know if that would be like a desirable existence to just live in the stock market universe, but it seems like there's
But
going to be
but
some wild stuff.
but you're feeling trends, and he actually did an experiment in the lab. They have this vest that produces like vibrations, and they had the subjects with like an iPad just making like yes or no decisions. They had no idea what they were actually doing, but they were getting feedback from the vest of whether or not that was a good idea or not. And at the end, he told them you were tied into a live feed of the stock market, and you were making buy and sell decisions, and you were feeling the trends of data. And they've applied this to like pilots too, of being able to feel the plane and give them a sense of these different things that are going on, and how the air pressure is affecting different things. And yeah, he's got a whole company called Neurosensory that's all or yeah, I think it's what it's called, but it's all about kind of giving the human mind and the human body new senses, new ways of experiencing the world. And it's all on the back of what we've been talking about. It's all on the back of the neural code and understanding the neural code.
Yeah, and I think maybe a good thing to end with, or maybe a second to last thing. A question from the audience, not our audience, but in the video that one of the videos that we'll put up of James Haxby's talk at Dartmouth. He gets this question from someone in the audience that's like, will this kind of understanding of the neural code allow you to one day basically just download information into your brain so that you could, have understand calculus at the click of a button, or any other subject? And he kind of he hedges on that. He's like, maybe it's in principle possible. I don't know, maybe, but I mean, it seems like in principle possible. What would you agree with that?
I mean, that's one of the really cool things that we didn't really touch much on, but the idea of learning. How is the neural code changing when someone learns something? Is this kind of concept that someone has that knows calculus, is it stable across other people that know calculus? And if we can really kind of kind of distill that and say, okay, this is calculus representation. Can we kind of create a neural code around that, that now we can kind of maybe feed back into the brain? Because one of the things we didn't talk about is that Neuralink, Elon Musk's wizard hat, is bidirectional. It doesn't just read information, it also creates activity. And so you could essentially kind of create patterns of activity. But I mean, this is all hypothetical.
Well, that's what we're all about on the Social Brain, exploring
Yep.
the brain and the future of neuroscience and social neuroscience. And yeah, I mean, I think this has been fascinating. I hope that the viewers think so too. Um, don't hesitate to send us comments or questions. This will be posted on both of our channels as well as our podcast, The Social Brain, which you can get on all major podcast platforms. And yeah, I definitely, if you're liked this episode, consider subscribing to both of our channels and the podcast. Like I said, we'll put the links to everything we mentioned, at least in the captions.
Yep. And if you want to support us further, my wife has a gift shop with cool data science and neuroscience type shirts and mugs and stuff. So it'll be in the caption on my channel too. So this has been awesome as usual. And feel free, if you have topics that you want us to talk about, reach out, let us know, because we're kind of building that library of what we want to talk about next. So
Yeah, and
thanks for
I've got
listening.
a poll going on the community tab on my channel. So if you want to throw an idea there, we've got a question posted there. So just post your suggestions as a comment, and we'll see if we can get to it in a future episode.
Awesome. Thanks, guys.
All right, bye bye.